So today I'm going to talk about information theory and applications to cryptography. This is sort of a theory of like randomness or uncertainty and things like this. It's less related to programming, but it's something I knew and I could present kind of quick. So again, let's review. Everyone taking a basic probability course, or remember what a random variable is, what an outcome is, and expectation, right? So we have a set of outcomes, right? So let's say this is omega, this is omega 1, to say like omega k. And the probability is just a value assigned to each outcome. So it takes as input an event and it assigns it to a real number, such that, and for shorthand, we're going to write P of omega I is equal to pi, right? So that's the probability the event omega I happens, right? And because it's a probability, we require that the sum of all possible events I equals 1 to k is equal to 1, right? So with probability 1, an event happens, right? This is, everyone good so far? Good, remember what these things are? A random variable, sometimes denoted RV, is a value assigned from an outcome. And sometimes it's just capital X. And capital letters are random variables. So value, sometimes the outcomes are the values, which is great, like points scored. What's the probability you get a certain score in, I don't know, pachinko or something. But for example, a coin doesn't have values. It has a heads or a tails, and those aren't values. So then you say, well, the random variable says heads is 0 and tails is 1. And then you have a value assigned for everything, right? The expectation, this marker was really strong, and then it's just gone instantly, is denoted by E of X. Let me go ahead and change, because these are good markers. I might as well spoil myself. Okay, the expectation of a random variable X is the average, or the mean, basically, right? So let's say this is equal to the sum of the event I happening times the value of I happening. Right, that makes sense, everyone? That's the expectation of a random variable. So for example, if X is an unbiased coin, so you flip a coin, it's unbiased. What is the expectation? Oh, and heads equals 0 and tails equals 1, for example. That's the random variable part. What's the expectation of X here? Half, right? So I could work it out. I could say we're going to take 1/2 times 0 plus 1/2 times 1 is equal to 1/2. Or you could say, well, all the outcomes are equally likely. I'm just going to average 0 and 1, which is going to be 1/2. So I've always liked this example because the expectation of a coin, if you flip a coin, the expectation is neither 0 or 1. It's just a half, which like doesn't make sense in like a real world setting because it's none of the possible outcomes, right? So it's a good example of why sometimes in statistics, mean is not a good representation of data, right? So if you tell someone who's blind, on average, a zebra is gray, that's not a good characterization of your data because it's just two extremals. But if you told them that the zebra was either black or all black or all white, you would at least be half right compared to gray, which is not right at all. Right. So what is entropy then? Entropy is assigned with all these so it's sometimes called Shannon entropy, or Shannon. The entropy is a measure of uncertainty or randomness. So these were characterized. This was all done by Claude Shannon, and he was trying to create a theory of how you could measure how many bits you would need to send over a channel if your channel had some error, and it would be a function of the error. So for example, if you're sending over a faulty wire and your bits have a 1/2 chance of flipping, there's not really anything you can do. But if there's like a 1/10 chance of flipping, you can just repeat each bit 100 times, and then the other party reads them in 100-bit blocks, and then they can decode, right? So, and it's literally a measure. Like if you, in like analysis and things, you can define a mathematical measure as a generalization of like a length or a area or something like that of an object. So it's literally in that sense a measure. So more entropy means more random, and exactly as defined, the entropy of a random variable is going to be equal to minus the sum of pi log pi, right? And this is actually just the, where did I write it? Yeah, it's just minus the expectation of the log of the random variable, right? So given this, what is the entropy of an unbiased coin, right? So let's work that out. Well, this is going to be 1/2, and we can bring this minus sign in here, so it's going to be log of 2, right? So we're going to have sum of I equals 1 to 2 of 1/2 log 2. And then each of these terms is independent of I, so it's just 2 of these summed together, so you're going to get log 2. So you can think of this, you can take the ceiling of the entropy of a random variable as the amount of bits you would need to send in order to encode it perfectly. The negative got brought, because this would be 1/2. So you bring the negative into the log, right? So C log A equals log of A to the C, right? So log of minus log of 1/2 equals log of 1/2 to the negative 1, which is equals log of 2. Yeah. Log, you guys remember that calculus? Right, so an unbiased coin has this much randomness. In your natural understanding of randomness, what is more random? An unbiased coin or an unbiased dice? Dice, because there's more sides, I guess, right? So what is the entropy of a dice? Well, we'll just say 6, I equals 1 to 1 over 6 log 6, right? Which is log 6. So I'm pretty sure log 6 is greater than log 2. So it's more random. That's the sense. Now what about what about a biased coin? So what is a biased coin? So here I had P0, P1 equal 1/2, 1/2. But let's suppose our coin is biased, and actually we can write this as like 1/2 plus epsilon, 1/2 minus epsilon. And then as epsilon goes from 0 to 1/2, right? So I could work it out, and turns out if epsilon is greater than 0, that implies that the entropy of this random variable is strictly less than log 2. So what is that saying is that if your coin has any bias, the amount of information it holds is less. The randomness it's less random, literally, essentially. So what about a deterministic coin? What about a coin that is always heads, you know? So to the intuitive understanding, what should the randomness of a deterministic coin be? Yeah, it should have 0 randomness, 0 uncertainty about the outcome. So what is that? We'll work it out. H of x is going to be 1 times log of 1 plus 0 times log of 0. Oh yeah, this is undefined. I forgot what the extremal points is, but this is 0. So, cool. And then I can talk about something called a joint entropy and a conditional entropy, which is going to be like, so the joint entropy of two distributions, two random variables, is written like this. So what this is basically it's going to be defined as the joint distribution of two random variables, which is like what you might expect that. If I were to write this out, I could write it out as minus the sum over the values of x, values of y, p, q, and this is the joint distribution for values x, y. Like it's like a bipartite kind of thing, and then the log of p times q at x comma y, which is basically what you would expect. But we don't have to consider all the things here. Oh, one more quick thing about this. If you were to plot this as epsilon goes from 0 to a half, you get a graph that looks like this. Right, and then here is epsilon equals 0. And then as it goes from 1/2 to 1/2. So another thing is it's symmetric immediately, right? Heads and tails are arbitrary, you can flip it. But the entropy is maximized at a uniform coin, uniform distribution, which makes sense. Anything less than that is going to go. So here's our deterministic coin, and here's how that works, if you were to plot the entropy. So this is the joint entropy. It's basically like both, quote unquote. The conditional entropy is written this way. So I'm going to write it as, what is the entropy of y? In a human sense, it's what is the randomness of y given that we know everything about x? So that's how we write it. And this is equal to, this doesn't matter, but I'll write it out anyway. P of value x for all x times the entropy that you're given that this random variable is this x. So basically it like fixes x, everything you know about y. And then the mutual information, which is the shared information between two random variables, is written this way. And I could define this with another ugly formula, but I'm going to write it this way. So this is all the information in h of x. This is all the information of h of y. This is going to be the mutual information of I, x, y. So this is what's shared between these two. What do these two variables share about each other? Then this minus this is going to be the conditional. So this is going to be h of y given x, right? And this is going to be then what? H of x given y. So then I could define this then as, what did I write it as? I can define it this way. I could say the joint entropy, which is going to be the union of both, is going to be equal to this, each of the two parts. So I'm going to add this, and then I'm going to add this, but we double counted the middle, so we have to subtract it off one time. So that's how you can define the mutual information. I can move terms around to get in terms of mutual information. So now let's talk about cryptography. What are we talking about there? I can erase everything. Everything's good. Nobody cares. Maybe I should have left this all up if it was going to be used as reference for everything I'm not going to talk about. But so in cryptography, we model adversaries a certain way. So you have to model your adversary. You say, what is the power of my adversary? What can they do? And then you prove something is secure relative to that model. So you could say your adversary, the common one is adversary, capital A, is a probabilistic polynomial time adversary. So what that means is probabilistic, it has access to randomness, and it gives us a non-trivial amount of power, so it can produce random numbers. It's polynomial time, which means it's bounded. So it has a certain amount of things you can do. The running time is polynomial. You guys, you know P and NP and all that, right? Maybe. It can't do exponential search, essentially, right? So like an example of what we apply like these models is in like semantic security. If we have X is event any adversary, I'll just say A, guesses the key. And this is like supposed symmetric key, a block cipher. Guesses the key of n bits. What is an upper bound of the probability of this happening? What's the probability that, the adversary correctly guesses the key? So they're trying to decrypt something. Yeah. So this is 2 to the minus n. Yeah. So it's just they guess a uniformly random string, and then they check if it's the key. If it is, they win. If it's not, they don't. But the probability that they guess correctly is this, because if you assume the key was chosen uniformly random of n bits. Given that, the definition of secure, so you have to, when you design these protocols, you have to say it's secure. And what you say is, well, we say it's secure if the probability of any adversary, any probable polynomial time adversary, whatever, so I'll just put a dot here, so I don't have to write all that, is less than 2 to the n. So what that means is that so you can write out mathematically something in human terms, any strategy an adversary could take is worse than guessing the key, which sounds like secure, right? If the best thing they can do is guess the key, then that means that's sort of a intuitive notion of secure, but then you can mathematically formalize it this way. So being a probabilistic polynomial time adversary is a common one, but there are other uncommon ones. So you can say, I allow my adversary access to an oracle, and they can have access some messages in the ciphertext space, or they can maybe the strongest model is then no restrictions, right? You could say, I want it to be secure against any adversary. Quantum, doesn't matter. I want them to be just totally off the rails. And that's a very high bar to achieve, but that's what we call information theoretic security. I'll explain some of that it depends. I'll give an example of why something isn't ever information theoretic, and I'll give an example of a scheme which is information theoretic. Yeah, so that's a great one, actually. What's it called? One-time pad, yeah. Right? So you generate a key of n bits. You have a message of n bits. If you XOR them together, well, that's technically information theoretic. But that has its own problems. One change in the ciphertext is a change in the message and things like that. Where was I going with this? Oh, right. So we say a scheme is secure against this if the mutual information of x and y is 0, where x is all private information and y is all public information. So basically, there's no shared knowledge between the private info and the public info, and that makes sense intuitively. And then you have now here a mathematical thing you can talk about when you do it. And then given that that Venn diagram I had, right, I could rewrite this as this is true. Well, I can just draw it again. So this is I, this is h of let's say x given y, and then yeah, so this is true if and only if the the conditional entropy of x and y is equal to the conditional entropy of x. So what this means here is, again in the Venn diagram thing, if you condition on y, it's going to be always less than x, right? So if you say h of x, this is always strictly greater than h of, right? So knowing something about y will always restrict the possible domains for x, always. You can't unlearn something, basically, is what this sentence says. But if you don't know anything about y, you're like sort of in this ambiguous maximal state, right? So this is true. And if these were to be equal, you have an equality. This is equal only if x and y are independent. And if they're independent, then the mutual information is 0. So given that definition of information theoretic security, let's talk about why public key cryptography is not information theoretic. So public key crypto. So what is public key crypto? It's ignoring all the actual implementations and schemes of it, a definition of public key crypto is this. We have 3 algorithms. We have a gen algorithm. So this will output a pair of keys, a public key and a secret key from a gen algorithm. there's an encryption algorithm. These are all polynomial time. These two must use randomness, and this one doesn't. So what the encryption does is it takes the message and the public key, and it outputs a ciphertext. Decryption takes the ciphertext, the secret key, and outputs the message. That is by definition a public key crypto scheme. And so just with this definition, and ignoring any implementations, RSA or what have you, no public key crypto system can have information theoretic level security. Why? Well, let's write it out. So what is X here? X is all private. It's symmetric, by the way, so I could do this, right? So I'm going to say, yeah, I'll just write it like this. So let X be secret info and Y be public info. It doesn't particularly matter. Okay. What is all secret info of in a public key crypto system? Secret key. From an adversary's perspective, what they don't know, sure they don't know the secret key, but they also don't know the, wait. I think I messed up twice. Yeah. Okay, X is all public info. And this is all private info. Okay, what is public info? Public information here. It's going to be public key. Yeah, the public key, the ciphertext, and private info is going to be the secret key and the message, right? But so what is the entropy of the public information? That's a crazy question, but basically what kind of domain could it come from? I don't know. It's non-uniform because it's like probably an English language sentence, but we know that h of x is certainly greater than 0 because there's got to be at least more than one message you're going to be encrypting. Given that, given all the private info, there corresponds exactly one message. So given the secret key and the ciphertext, did I do this right? I think I messed up. Given the, so what is basically the entropy of the message given the ciphertext and the public key? This is equal to 0. Right, so because invariant of any algorithms that exist, there corresponds, given the public key and the ciphertext, exactly one message. So this is 0, I think. Hope I worked that out right. Anyway, so no public key crypto system can have information theoretic level security, simply because of this. But it doesn't matter in the real world. Public key crypto is way too useful for things, and we don't really care about this sort of highest stratospheric level requirement of things. So that was an example of a scheme which does not have information theoretic security. Let me talk about one that does, and that is threshold secret sharing. So I'm just going to do this. Maybe you guys can see the bottom of the board. So threshold secret sharing. So what that is basically you have, and sometimes it's written as T of n SS. So you have n players. Any T of them should be able to reconstruct the secret, but any less than that should not be able to. So, for example, what is an n out of n scheme for this? if you have some secret S and you want to share it among n people, and they all have to come together, and only when they come together can they unlock the secret. This is sort of like, you can imagine like, you know how like nukes and stuff have multiple keys, right? You don't want 3 of the people to come together and nuke something when you require 4 keys, right? So an n-out-of-n scheme would look like this. This is sort of an, I'll talk about how to construct a t-out-of-n scheme, but just as at the upper limit, we have what? That S is our secret. X1 through xn minus 1 is equal to random strings of length. So I'm going to give n minus 1 players a random string of length n, of length the size of the secret. Then the xn, the last player, is going to be computed to be the XOR of all the other things and S. So I'm going to XOR all the random strings and XOR S together to compute the last one. So now I have all these random strings, and then there's suddenly the last one is dependent upon S. So then if they all come together, they XOR their strings together, they're going to get back what? If you XOR both sides of this was xn, you're going to just get S, right?
It's commutative.
Yeah. So this is probably poorly explained, but does that make sense to people? I hope so. Any questions? I'm not sure I did a good job explaining that, but is that convincing? If you take n minus 1 random strings, the last player is dependent upon S. It's just S XOR the random strings. So when they all come together and XOR their strings, all that's left is going to be S, right? Maybe I write it this way. What is the XOR of x1 I equals 1 to n is equal to the XOR of n minus 1 I equals 1 to xi XOR x1, which is equal to the XOR of I equals 1 to n minus 1 xi, and then x1 is defined here is going to be XOR xi n minus 1 I equals 1 to n XOR s. So if you XOR a string with itself, you get the string back. So that all cancels, right? And this would have been x1, right? And then all that's left is S. So yeah. So if you have n players and if you need all n, it works out great. But if you have less than n, you have to do this scheme called Chalmers secret sharing scheme. I'm not going to get extremely elaborate in the details of it, but I'm just going to try maybe appeal to your intuition, so to do as little calculus as possible. So I'll call, I guess, calculus. How many points define a straight line? How many? 2. So 2 points define a line, right? A unique line. There's given any 2 points. That's actually like you can go to Euclid. Any 2 points, there exists exactly one unique line through those 2 points. Bam, bam. So I give you 2 points, 1 line, right? You can generalize this. If I only give you 1 point, though, there's infinitely many lines that go through that 1 point. But as soon as you choose the second point, you fix the line. So what about how many points define a quadratic? So we have some x squared. So we have like ax squared plus bx plus c. So a polynomial of degree 2 is quadratic. How many points define a quadratic? How many points do you need to be unique? 3, yeah. So if I give you 2, for example, I can always do something like this. Right? Something crazy. But as soon as I choose a third point anywhere, it's fixed. So to generalize, you need n plus 1 points. And n plus 1 points uniquely define, I'll say fix a polynomial of degree n. So that's our scheme, basically. Here's Shammer's secret sharing scheme. So basically what we're going to do is encode, and this is a super generalization of it, but I hope you guys get the idea. Encode S into some polynomial, we'll call it f of x. And you could say, well, I break it up into bite-sized blocks and I put it in the coefficients or something, right? There's a way to do this. And this is not over a real plane like this, it's over some finite field. So basically that means like we mod out by something. So you roll over and you can't do any nice like derivatives or something crazy. So encode S into f of see. And the polynomial f of x, so f of x is degree what? T minus 1, right? So choose n points of f of x, distribute to n players. So that's the scheme. And I'm missing some details and stuff, but that's like the main idea, right? You could choose the points like I, f of I, and you can order the f of I. So this would be like f of 0, f of 1, f of 2, and so on. If you wanted to have some more ordering for things, and it's not stuff I care about. So then you distribute the n points to n players, and if any t of them come together, they can, because the polynomial is degree t minus 1. So if any t players, players come together, they can learn f of x, and I'm going to put a star here, and learn the secret S. So I put the star here because I haven't described how, given t points on a polynomial, how do you construct a polynomial? If you know you can construct a polynomial of degree whatever, how do you do it? There's a name for it. Does anyone remember? It's called Lagrange Interpolation. Has anyone have to see that in a class at all? Maybe? No. Okay. It's this like recursive algorithm where you take 2 points, you multiply, and then you add a third one, and that gives you a degree 3 polynomial, and you just keep applying it this way. It runs in polynomial time, so it's like efficient and stuff. This is Shammer's secret sharing scheme, essentially, and it's basically like optimal and stuff. People are still proving bounds on it, like how good is it, why is it, the share sizes are really nice.
Are there any problems if the endpoints are not unique? I guess it just kind of, like you lose, but if those two players come together that have the same points. You know.
Well, if you choose your points this way, so this would be, for example, 0, f of 0, 1, f of 1. So, right, and this is a curve.
So you index your players, basically.
Yeah, exactly. So that would solve that problem. Even then, if this is a large enough field, it's very unlikely that you were to choose random points that they would give you the same. You would give the same one.
Are there any problems with Shamir secret sharing that should be addressed?
There are some like calculus tricks if this is not a finite field that I remember, and also because it's a computer anyway, you have to do it. There's no real plane in the computer, right? It's like a giant calculator, right? So you have to do this anyway. But if you don't do this, there's like, you can do a polynomial amount of searching if you have n minus 1 points, right? So if you have, this is all like math, but if you have a function like this and you don't know the last one of the points on it, you can sort of approximate it by bounding all the other points. So you can say, well, it could be possibly something like this. You know, you can guess, and then you can take the range here, and that's actually a polynomial amount of searching, something like this. The distribution of the last point is a function of the bounds of the previous points. I don't remember anything else about the issues with it. Maybe there are. There's a lot of work on the size of the share, right? So like like each share, how many bits do you need to encode a point? The upper bound is like n over log n. I'll write it this way: size of s times n over a log n, and then the lower bound was recently, it's like log of t plus 1, log of the size of s t plus 1. And so it's somewhere between linear and logarithmic, the size of this thing. Right. Oh, the important part. Why do you care about this? Actually, this trivially has information theoretic security. So, what is the mutual information of the message given t points? If you're given t points, you can reconstruct the polynomial, you can construct the message, so this is 0. But what's the mutual information between any t minus 1 points? So t minus 1 points don't tell you anything about the message, nothing. What that means is these are independent. So this is literally equal to, it's certainly greater than 0. Did I write it down? Well, this is equal to the joint distribution of the message given t minus 1 points minus the entropy of the t minus 1 points. Well, because these are independent, you can just kind of pull it out. So this is just equal to h of m, the entropy of the message minus the entropy of that. Which is whatever this is. This is greater than this, so this is greater than 0. So Sharma secret sharing here, given just to reiterate, given t minus 1 points, you're trying to construct the secret. You have zero knowledge. Zero knowledge is a bad term here, but you have no knowledge of the last point. All of them are equally likely. Any point in the field could be it, because there exists a unique polynomial through your t minus 1 points and all the other points. So because each outcome is equally likely, we have this sort of mutual information trick here. So I think that's everything I have. That's basically it. So in summary, information theory is kind of powerful stuff, but in the real world, it's less practical. We don't really care about having information theoretic security because we can't even imagine an adversary with this kind of computational power. Sometimes instead of information theoretic security, it's called unconditional security. So a lot of times proofs are dependent upon some conditions, like for example, integers, and you can't factor your integers in polynomial time or something like this. But this is not dependent upon that. So even a supercomputer or whatever, there's no universe that could break something like this. But you can imagine an adversary given exponential search could encrypt every single message with the public key, find a matching ciphertext if there was no randomness. But actually, even given all the randomness, it's still search. So I think that's everything I have. Is there any questions? Anything?
Where's that entropy play into key generation for your signature scheme secrets?
In practice, people don't care because it's always uniform. So the uniform, what is the entropy? If X is always uniform, this is going to be sum of n, I equals 1 to 1 over n log of n, which is just equal to log of n. So entropy is maximized at the uniform level, right? So you can imagine an n-dimensional concave object that looks like this instead of a two-dimensional one. There's always going to be a maximal point. And nothing will get higher than that. So in practice, all key generation is like this. So it's easy to get uniform random bits. It's actually difficult to get in the practice to draw bits from a non-uniform distribution. Because randomness is, usually when you generate randomness, you don't want it. It's just, static electricity and things like this.
Any more questions? One thing about Shimon secret sharing It is actually like used in the wild quite a bit, but one of the things you want to be really careful about is the fact that you are actually recreating the secret. And so, if I do if we're doing secret sharing between us, and I do my part and then send it over to him, he can now generate the secret and he can just save it somewhere. And so once the secret's recreated, you can just save it. So you want to be really careful about that when you're applying it. And there are some other schemes where you're just signing stuff and aggregating signatures that avoid attacks like that. But you have to be really careful about making sure that no one has access to the secret. So a lot of times it's used in like semi-trusted setups where you have like a corporation with N people and they all have this one super trusted computer that can be that one that generates the final secret, and then they all can see that, okay, it's gone now.
Yeah, someone has to see the secret in order to generate the points. So, and then you have to trust they did this in an honest way, right?
But usually it's just a lot easier to go with the signature route, and you'll just use Shamirs for your own private information. So you just use Shamirs if you want other ways to back up your secret info. Because with signatures, it's just per message, so you don't worry about sharing the results.
Yeah.
Oh, one last thing is I forgot to give this example. I saw this in the wild of a 1 out of n secret sharing scheme, and what that is you had these locks, and instead of a chain, they were closing a fence. They just had one lock as, okay, this is going to be really ugly. They just had literally a loop of these. Okay, so this is a set of locks that close some gate, and then every janitor or whatever had a key. So any lock will break the chain. If you break one lock, you break one link, the whole loop is broken. So that's a 1 out of n secret sharing scheme, right? Every player has one share as a key, and any player can access the secret and open the door. So that's kind of an interesting thing. And then you can actually do some exponentially more locks, and you can create a T out of n physical secret sharing scheme. So.